Hi there and welcome to Workshop 6. So today we're going to be looking at neural networks, and it's split into two sections. We're going to start by looking at the same example that we looked at in the previous workshops, where we're trying to predict the target user variable in the comp data. And then later on there's a prediction exercise where you take some new data and you have a test set which doesn't have the outcome variable. And then you try a bunch of models and see how well you do. Find the best model on the validation set that you have, and then you predict on the test set the unknown outcome and send it to me, and then I'll let you know how well you did. So we'll start by reading in the data and running the first model. So you can see here when we set up the model, there's a couple of things that are a bit different. So we have our usual sort of syntax here where we've got a formula indicating the model form, and then we've got our data set, our training data. But we've also got these additional parameters. The linear equals true means that we don't want a transformation on the outcome. So by default, NNet will transform the outcome variable to be between 0 and 1 because it's also used for prediction. It's also used for classification, where your outcome variable is a probability. In our case, the user variable is not on that scale, so we don't want a transformation at the outcome variable. And the second one is the size, and you remember that the rule of thumb for the number of hidden nodes, which is what the size represents, so the number of nodes in the hidden layer, is the effective number of predictors divided by 2. So in this case, we've got 21 numeric predictors, so they're all worth 1. 21 over 2 is 10.5, rounded up is 11. Okay. Note that we've set the random seed here because to simply make it reproducible. So by default, NNet will set the weights or the coefficients of the linear transformations that are used inside the neural net. It sets all those coefficients to random values between minus 0.5 and 0.5. So each time we run it, we're going to get a different answer. So if I comment out the set seed there and run it a few times, you can see that we're getting a different answer. And we generally don't want that because we want to make sure that any changes we make are due to the underlying thing that we're changing. So for example, if we muck about with the size variable here, we want to be able to determine when we actually improve things. And we don't want that to be affected by the random seed that we start with. On the other hand, we don't want to choose a model based on the random seed, right? So we don't want to for example, choose a particular value for size, or to choose to go with a neural net over a random forest or whatever, which is just down to the getting lucky with the random seed. We want our model to be able to generalize to other data sets. So you do want to try fiddling around with the random seed just to make sure that the performance of your neural network is actually quite similar from random seed to random seed, and that you're not sort of overfitting the training data based on a particularly lucky or particularly unlucky choice of the random seed. Okay, so same applies to a random forest, right? Where the splits of the data that are used to determine the bootstrap samples for each tree is random. Now we're going to get predictions for that model now. So we'll do this in the usual way. So we're going to bind our predictions. Model1.nn. Is that what it's called? Let's have a look. Model1.nn, yes. And we'll do prediction on our comp test data. Okay. Now you may find that the outcome variable here is has an extra, so it has like square brackets and a comma and then a 1 next to it in the name, and that's what was happening to me earlier today. And it's because the outcome from predict.nnet is a matrix, and it's a matrix with just one column, and bind cols may or may not detect that. I'm not quite sure, I can't seem to reproduce it now, but if that happens to you, then just add a as.numeric to it. Okay, you'll get the same thing whether it happens or not. Okay, and one thing you'll notice is that these predictions are very, very poor. Okay, we're predicting essentially the same answer for 9 of the first 10 rows, and the one that we're predicting a different answer for is actually slightly higher than some of the other entries, and we're predicting a lower value. So we seem to be getting very poor predictions here. And we can, of course, check that. By doing our computing the mean square error. So we're going to go user minus our prid squared. There's our mean square error, and you can see it's quite high. This is much higher than it was for the previous models that we've done. We could also, of course, use yardstick for this, so we could use metrics with the truth equal to user and our estimate equal to pred. Okay, and it'll give us the root mean square error, for example. So we can see that that's the square root of that 51 number that I had before. So this is not performing terribly well. So one thing we might want to try is modifying the decay of the model. So when you fit a neural network, it uses what's called the backpropagation algorithm to estimate the weight. So essentially what you do is you initially define the weights to be random, and then you forward propagate all of the training data through to the outcome variable. Okay, and then at the outcome you then have the true value on the training data, and you essentially compare them. So you find out how far out you are for each observation, and then you propagate that error back through the network. So you take it from the outcome, you propagate it onto the weights. So you can go back to the hidden nodes, and then you propagate it back to the weights on the input nodes. And you do that essentially by looking at the gradients. So if you look at you've got your model formula, therefore you can compute your log likelihood from that. It's basically a bunch of function composition, right? So you've got a linear transformation, then you've got your activation function, which is maybe a sigmoid or something, and then you've got another linear function. So that's function composition. So you can maximize that function by differentiating it in order to find the gradient, so that when you propagate your error back, you're moving towards the area of low likelihood. So you're moving towards the area of high likelihood. So you're moving towards the area where your weights are optimal. And so that's the backpropagation algorithm. There's plenty of pieces of information if you're into mathematics and you know things like the gradient operator and so on. There's plenty of resources on the internet to find out a few more details about that. You can start with the Wikipedia page, for example. Right, so we're going to fit a new one now where we change the decay parameter. So in the backpropagation algorithm, essentially you that tells you which direction you need to move each of the weights and by how much relative to each other. The decay parameter is how much you move, right? So essentially, because when you're moving those parameters, you're only using gradient information, so you're only using local information about the shape of the log likelihood surface at the point you're currently at, and you're only using first derivative information, not using sort of how it's bending. So you only know I need to go up the hill or down the hill, basically, and sort of how steep the hill is. You don't want to overshoot the top of the hill, right? And so the decay parameter is how much you move. So setting a lower value will tend to make you move a little bit slower, so you may reach a slightly different maxima, for example. So we're going to try that. Let's set the seed the same as we did before. Okay, and we see that we've reached a lower. This is essentially a measure of the loss, so a measure of the accuracy of the model and the training set, if you like. So it's similar to sum of squares, really. So you can see we reached 28,000 here, and we've got down to 15,000 here. So this is a much better fit for the training data, but you can see that it stopped after 100 iterations, whereas this one up here converged. Okay, and that's just because we're moving slower. Okay, so with each iteration of the backpropagation algorithm, we're moving towards the peak of the hill and a lot slower because we've specified a smaller value of decay. So we can change the number of iterations. So by default, it stops after 100. We can change that with maxit. short for max iterations. Okay, so we might try, say, 500. It defaults to 100. Let's try 500. And you can see we're getting a lot better, but we still haven't converged. Okay, I suspect we're overfitting here, but let's see. Right. Okay, so we've converged there after 760 steps. Now, one thing you should notice is if I change the random seed here, I will get quite different behavior. Okay, so here I converged again in a very short period of time. Oh, there's a long one. Okay, so you can see that where I converge, the number that the loss that I end up with there is actually quite different depending on the random seed. So here we've got a big run where we're getting a very, very good fit. Okay, and this is basically the neural network overfitting. So let's see what happens. So we'll maybe compute the mean square error here as well. So we'll use the same code that we had before. No point in me typing all that out, but again, let's just take that. So we're going to use our second model now. And you can see here that the root mean square error is in fact quite a bit better on the test data. You might want to see what it is on the training data as well, because you'll find that it's improved a whole heap on the training data. Okay, so that's how to fit it with the base package. Let's have a look at fitting it using parsnip instead, so using the tidy models framework. Okay, so we can set up the model specification for that previous engine using the MLP. So this is going to be our spec 2. So the size parameter is named hidden units, which is a little bit more informative as to what it does, and the decay parameter is named penalty, which again is more informative as to what it does. It basically penalizes the amount that we move at each step. Okay, and then we can use our usual setup with fit to do the model fit. And then our usual prediction stuff. So we can just take our comp test, we can just take our model fit and we can augment with our new data as our test data. And then we can do our metrics. In the usual way. And now notice I get a different answer here because of course I haven't set the random seed, have I? And I've also not specified the number of iterations to use. So if, for example, we have a look at we extract our fit engine. There's our neural network that we're fitting. And then if we pluck the convergence, sorry, I've got to put that in quotes, we see it's 1. So let's have a look at the help for neural net. Okay, and if we look at the outcome object, the value object is of class nnet, and one of the things that it has there is convergence, and it's 1 if the maximum number of iterations was reached, otherwise 0. So 1 means it did not converge, and 0 means it converges. So that's where this knowledge of this is where I got that pluck from. Right? You remember pluck is just to pull out a value from that class. So we haven't converged, and of course the reason we haven't converged is we don't have the correct number of iterations, which is specified by epochs in the tidy models framework. So if we run that, this time it has converged, and we see we get a estimate there, which is the same as what we had before using the standard framework. Okay. Now the advantage of this, of course, is that we can use augment, so the prediction is a little bit simpler, and we don't have that issue, which unfortunately I couldn't reproduce for you, of having to pull out this as not numeric. So predict returns a matrix. You can, if we look at the help for predict.nnet, you can see that the outcome variable is a matrix of values returned from the trained network. And of course, the augment function will take care of that for us, right? Parsnip is built to ensure that the outcome variable from predict or from augment is always the same class. So it's going to take care of that for us. Okay. Now, with our original model, we had very poor predictions, and in fact, with this model, we're going to get poor predictions as well, depending on the seed. So here we've got okay predictions. Let me remind myself what the predictions were for the other models. So let's have a look at our Lab 5. What did we get for Lab 5? So we had a tree prediction of about 3, and then our forest is getting to another. So forest is getting about 2.5. Right. So the neural network's doing around about the same as the forest, slightly poorer than the forest. But this is dependent on the random seed, right? If I drop that random seed out and just rerun this code, then I get much poorer estimates. Right, so I'm getting a lot of variability from run to run. So my model fit, you can see I got a good one there, it took a bit longer, right? It's highly dependent on where I'm starting. So it's highly dependent on the random seed, which is not good. And the reason for that is that where you start depends on those random weights, and those random weights are used in a linear combination of the predictors. And if you remember what this data looks like, they're on vastly different scales. So when you're working out the linear predictor, what you do is you take a number between minus 0.5 and 0.5 times this one, plus a number between minus 0.5 and 0.5 times this one, and so on and so forth. You can see that these ones here, you know, if we generate a random weight of, say, 0.1, then when you multiply it by this number here, you get to 16,000. So this is dominating that linear predictor. And then you remember what happens is that we then transform it with a sigmoid, right? And you remember the shape of the sigmoid is such that once you get past about plus or minus 4, essentially your outcome from the sigmoid is either 1 or 0, right? If your linear predictor produces a number that's less than minus 4, then your outcome variable is essentially 0. And if your linear predictor produces a number that's bigger than 4, then once you transform it using the sigmoid, essentially you get 1. You're so close to 1 that you can't differentiate it from 1 at some point, right? And our linear predictor here could be in the range of plus or minus 10,000 or something. So at that point, when you transform, you're just getting the number 1 or 0. And when you change those weights, you're not changing the outcome, because you're so far away from 0 to begin with that even when you move the weights by the backpropagation algorithm, you don't move the answer, therefore the neural network has converged. Okay, so the problem is that these variables are on very large scales. It's not really a problem that they're on different scales, it's more a problem that you've got some variables that are very large, so that when you do the exponentiation that's in the sigmoid function, essentially you lose precision in the computer, right, and you basically end up either at 0 or at 1. And changing things does not change the outcome variable. Okay, so this is explaining that process. You can see that the maximum value of the rchar and wchar variables are very high. And of course, if we exponentiate those, we get essentially plus or minus infinity, right? So we need to scale these down to something small before we start, Okay, so we're going to use the recipes package for to do this. This is sort of shows you a way of doing it, right? You could compute the, so you could take the training data, you could get rid of the target because we don't want to scale that, and then you could essentially compute the means of each column and the standard deviation of each column, and then use the scale function in order to do the scaling. Right, so if we have a look at comp train scale, right, everything has now been scaled, right? So they're all on a similar, so they all have mean 0 and standard deviation 1. Okay, so because they're all on a similar scale, now when we, and because they're all small, now when we multiply this by something between minus 0.5 and 0.5, it's still going to be small. So when we exponentiate the sum of all these things, we're not going to get a too bigger or too small a number. Okay. So this is a little messy, but it's doable, right? Remember that we'll need to scale the test data in the same way. So we'll need to rerun the same computation here using these same values, right, in order to scale the test data as well, which is fine. You can see that it's a little messy because scale returns a matrix, which we then have to transform back to a data frame. Luckily, when we do so, the names are preserved for us, but it's still a little bit messy. We could also do it by staying in the tidyverse framework, but in order to do that, because we're wanting to apply a bunch of different operations to different columns, we're going to need to do pivoting, right? So you can see here that we take our training data and then we pivot everything except the target value to a new column. So this is the same trick that we used for when we plotted the user versus all of the other variables, right? The idea is that you convert it to long form, which is untidy, right? So you have for each observation of the user column, you have a name column and then the value column, right? You then group by name and compute the mean, right? So that you get essentially the mean and standard deviation for each variable. Okay, and then you could apply it to the training data in the same way, where you take the training data, you pivot it longer, you add a row ID so you can pivot it back wide later. You remember we have to add a row ID because otherwise, if the user variable is the same across multiple observations, then it won't know which one to pivot back. When it pivots, all of those things will be compressed down to one row, which you definitely do not want. So we take our training data, we add a column, and then we pivot longer. We add the row IDs and we pivot longer, so we get this form here. And then we're going to join in our training data, our scaling data, right, so that we have the mean and standard deviation, so that we can then, for each value here, we can subtract the mean and divide by the standard deviation. So that's what this mutate is doing. Right, and we just get our scaled value, and then we pivot that back wider. To get the same data set, and then we drop the row ID. Okay, so here's our scaled data. You can see that this is quite a complicated process. It's easy to make a mistake here. I think it's actually easier to do in base R, so this is using the apply and the scale arguments, than it is in the tidyverse, because we have the requirement in order to dive things longer in order to make this easy to do across multiple columns at once. You can do it while staying in wide format. It's just that the way you'd have to do it is a little bit more broken down. So you could use mutate across in order to do the same operation on a bunch of different values, but getting the different means into it would be a little bit difficult, I think. So that's why I pivoted longer. So we're going to do this and we're going to do this also to the test data. So let's do the tidyverse version. So we're going to create a scaled version of our test data, and all we have to do, of course, is just replace our training data with our test data. We're still going to use the same means and standard deviations which were computed on the training data, but everything else is then the same. So now if we have a look at comp test, okay, there's the scaling there. Okay, now it's super important that the scaling is the same, right? We don't want to repeat what we did and compute a new set of scaling information from the test data, because we need to make sure that we apply the exact same functions that we apply on the training data to the test data. Otherwise, essentially you're applying different models. So when we go to do prediction, the transformation that we've used is going to be different. So our values for L read, L write, and so on are not going to be equivalent to what they were in the training data. Okay, so let's for another neural net, we're just going to take the same one that we did before. This one here, and now we should find that it has it's not quite as different from. Right, so this is going to be our spec 2 is going to be the same, but it's going to be spec fit 3. Okay, so we're going to use comp train scaled here. And then we're going to see if we converge. No, we don't. So we're going to need a few more epochs. Let's set the same seed so that we can compare. Still aren't at convergence, so let's go a little bit further. Okay, we're converging now. When we do predictions, we're going to have to use the test scale set. And here's our estimate here. And hopefully this shouldn't vary quite as much from run to run. So if we comment out the seed and rerun it, it's going to take a wee while because we've got a lot of epochs, but you can see here that our estimate isn't quite as bad as it was before, and it isn't jumping around as much. Okay, it's still jumping around because we've still got randomness involved here, but it's not jumping around as much as it was before. You remember we had much poorer estimates as high as 7 for root mean square error before, whereas now they're sort of 5 and lower. They're still not as good as the random forest. But it is better. Let's set our random seed back in and see where we get to. You can see we've got a bit better than we were before. Okay, so the general lesson is that if your variables here are on very different scales, then you need to scale them. You need to scale them down, or, well, if your variables are large in magnitude, then you need to scale them down, okay? And you can scale them any way you like you could just divide them by 100,000. You know, if they're in the 100,000s, then divide them by 100,000 so that in the range, you know, minus 10 to 10 is fine, okay? But nonetheless, having a sort of a process for doing so is useful, which is what the recipes framework does, right? So here we're going to set up a recipe, okay, where we give it the formula and the training data, and then we're going to normalize all our numeric variables. So you can see here that we've got centering and scaling for all our numeric predictors. Okay. So the recipe basically, it's kind of like baking, right? So the recipe basically gives the steps that we want to perform, and we can add lots of other steps in here that we want to do, but generally we're going to be using it to do scaling. And then once we know our recipe, we need to do our prep. So we're going to prep based on our training data, and what that does is it works out our centering and scaling for all of those variables. Okay, so it has trained the values. It hasn't actually done the scaling yet. All it's done is use the comp train data in order to figure out what the scaling should be. Okay, and then we bake. Okay, so bake then takes that recipe, applies it to the data set that we give it, and gives us our outcome variables. So here, our comp train baked is going to be our scaled data. Okay, notice that our user variable has not been scaled, because we asked just to scale all of the predictors, not the outcome variable. And in the same way, we have the test data also baked, and that will be using the exact same scaling that we used before. Okay. So we can check this by using anti-join. So if we join it to our training, our scaled data that we did manually, we can see that we get no rows returned. Right. So you remember anti-join returns rows in comp train baked that aren't in comp train scale, and it's returning no rows at all, which tells us that these two data sets are identical. Okay. So the recipes framework just gives us a nice, tidy way of performing that data processing that we need to do before we fit any model. Now, the scaling that we've done is just a linear transformation, right? So all we've done is we've subtracted the mean and divided by the standard deviation. So that should not affect any of our models, right? So because it's a linear transformation, when we bung it into a linear model, we will get the identical output. It's just that our coefficients will be different in the linear model because we've scaled things differently. Okay. Similarly, in a decision tree, in a regression tree, or a random forest, we will get the same results. It's just the splits will be scaled accordingly. Okay. So you can always choose to scale your data first. So start with a recipe and bake your data right at the start, if you're thinking that you may need to use a model that will require the scaling. Okay, which the neural network, of course, does. There's other things that require scaling, so it's often advantageous to scale for when we're doing k-nearest neighbors, for example. Okay, so the recipe to fit a model would be, steps to fit a model would be to use a recipe to set up and prep it on the training data in order to define the scaling, then create a model specification, fit the model on the baked training data, predict the model using the baked test data, and bind it to the test data, and then can evaluate it using metrics. So this is the type of setup. I guess we could optimize this a little bit, right? So here's our recipe, okay, for prepping the data. Okay, so we tell it which variables we're going to want. So that's what that first step is, basically just telling it what the name of the variables are. And then we're normalizing all the predictors and prepping it. So that's computing the scaling coefficients. Then we set up our model spec, and we fit the model on the baked training data, and then we predict on the baked test data, and then we evaluate our metrics. Now, the advantage of doing it this way is that when we're doing our prediction, we're binding it to the original test data, the unscaled test data, right? Because the prediction is using the scaled data, because the model was built using the scaled data, but that doesn't mean we have to use the scaled data for when we bind our predictions. We can bind it to the original data set, which can be useful for visualizing. So, for example, if you want to visualize your predictions versus one of the variables, you really want to use the original variable and not the scaled version, because the scaled version you'd then have to detail what the scaling was, whereas perhaps the original variable was on a sensible scale to begin with anyway. Okay, so this is the advantage of doing it this way. Notice that we could optimize this. Instead of bind, cols, and predict, we could just use augment to do it all in one step. Right, so we could instead rewrite this as just take out fit and augment with the bake. Right, and so these are our model steps. Okay, and the nice thing about these model steps is that when we want to switch out the model, we just change this line here. right? Everything else does not depend on the model type, right? We can set up our data in the same way with a recipe that applies to all model types, because this is just normalization. We're not doing anything. We're not transforming the data in different ways. So we're not doing log transforms or something like that, which may or may not be appropriate depending on the model we're fitting, right? If we've got a linear model, maybe we want to do a log transform with the outcome variable. But if we've got a tree or a forest, maybe we don't need to. Okay. Everything else is the same, right? The fit procedure and the testing procedure is exactly the same for all models. So to switch things out, all we do is switch that one line of code, rerun it, and we can fit a different model. Okay, so rerunning the code a few times gives us different metrics. Okay, notice that some of them can be very poor. I had a 9, I've got an 8, and that of course is because the neural net isn't actually converging. Okay. So if we could fit that, we could check that by pulling out the extract the fit engine and then pluck convergence. Right. Each time we run it, it's not converging. So we could fix that by adding more epochs, and then we'll get convergence some of the time. Not then, not then. Maybe we'll never get a convergence. We need a bit more epochs. Let's try 5,000. Okay, we got convergence then, but still didn't have a particularly good fit. We got convergence then, we got a better fit. Okay, so my take-home message from this is neural nets really aren't great for this data set, because I'm getting quite different fits. So there I got a very similar fit to last time, but sometimes I'm getting quite different fits, right? So the neural net on this is unreliable. And the reason really is because the neural net is super, super flexible, right? Here we're setting up so let's extract the fit engine. Just run that. Right, you can see we have 254 weights. So we've got 254 coefficients that we can play around with in order to optimize the fit. So essentially what we're doing here is we're trying to optimize a function in 254 dimensional space. So there's a lot of direction, a lot of flexibility for us to move through that space and find an optimal, find a sort of a hill, if you like, try and optimize the loss or the log likelihood in that space. And there's going to be lots of little hills all over the show, because there's going to be lots of combinations of those weights that lead to a pretty good fit. And so finding the best fit is going to be real hard work, because there's so many different directions to move in, and there's so many different sort of locally optimal hills that we're going to find ourselves moving towards all the time. Okay, and that flexibility has results in a really hard thing to optimize. So a lot of the time we're ending up in local optimum. We're ending up in a local optimum, but it's not necessarily a global optimum. So we're not finding the best neural network. What we're finding is a neural network that does reasonably well. Okay, and this is generally a problem with neural nets. Okay, and there's a lot of work being done to try and fix this problem, because there's so much flexibility in these things that they can often that they're subject to overfitting. So often they'll do too well on your training data and then won't generalize well to independent test sets. So there's an example of that in the lectures. And there's that problem of it highly depends on where you start. Okay, so running it multiple times gives quite different answers. You do get this problem as well with some other models. So you do get it, for example, with a random forest because of that randomness built in. but it tends to not be anywhere near as much of a problem as it is here. Okay, and it does depend on the situation. So, for example, one way to reduce the amount of variation from model run to model run is to reduce the number of weights. So, for example, if we drop the number of hidden nodes, okay, then if we have a look, now we've only got 116 weights, right? So there's a lot less flexibility, and we got a better fit. Whether we consistently get a better fit, it seems as though we are doing better. It's not as consistent as the other model types, but the fit overall is actually getting better. So that's another parameter that you can optimize. And sometimes it's worth going for a less flexible model with fewer hidden units in order to make sure that you get a more stable prediction from model run to model run. Because of course you don't want to be relying on a model that is dependent on the initial random seed. Because essentially that's a model that is probably overfitting to your training data and therefore won't go well to your test data, won't go as well on your test data. Okay. Right, so we could just write a few notes here. As the model, as the a large number. Okay, so that's the basic idea. Right, so for the rest of this, we've got a prediction problem. So we've got some bank data. Let's have a look at it quickly. So here you've got a bunch of variables that have already been scaled. You've got a Q variable which hasn't been scaled, and what we're trying to work out is the rejection. So that's going to be our target. And what you have is we also have another data set, bank predict me, which has the same predictor variables but does not have the outcome. So your goal here is to fit a range of models on these data and try and find what you consider to be the best model. And once you've found the best model, you can do prediction on this predict me data set and then send me the predictions. Okay, so send me the the predictions as a CSV file. There's my email address there. And I'll tell you how you got on. So I have the same data set, but with the true outcome variable. So this is a problem where we have a true test set. Okay, we don't know what the outcome variable is, or you don't know what the outcome variable is. I do. So you need to build models using just this data set for which you know the outcome. So split this one into two, split it into a training set and a validation set. Fit a bunch of models on the training portion. Figure out which one does best using the validation portion. You can tune those models if you like. And then once you've decided on the best model, refit it on all the data, and then do prediction on this data set and send me your predictions as a CSV file. And I will then take a look and let you know how well you did. Okay? Have fun with that.